Okay, so now let's prove a very simple theorem about convergent sequences, which is that they are bounded, which is hopefully not too surprising. First, before we do that, we haven't technically defined what it means for a sequence to be bounded. We've defined what it means for a set to be bounded, but it's a very simple idea. So we say a sequence Sn is bounded if the set of values, okay, maybe I should say, this is, kind of assuming that Sn is indexed starting from 1, but obviously you can adapt this definition for any way of indexing the sequence. That's going to be just true in general. So we're going to be stating a lot of stuff for sequences that are just indexed starting from 1, but like it's totally trivial to just modify any of those statements to allow for any starting index. So if the set of all values, this is the set of all values in the sequence, all the terms, right? If that set is bounded. Oops. Equivalently, Sn is bounded if there exists an M greater than 0, say, though it has to be greater than 0 for this to make sense. Or I guess it could equal 0, okay, such that Sn is, but obviously if there is a bound equal to 0, then you can choose one that's greater than 0 anyway, such that the absolute values are all less than or equal to M. Yeah, for all n. So this is also like slightly different because here, I mean, it's not really different, but it's phrased differently because here we're using a single bound as an upper bound on the absolute values. That's the same thing as saying that M is an upper bound and negative M is also a lower bound on the actual values themselves, not the absolute values, right? Just the numbers, the raw numbers. M is an upper bound and negative M is a lower bound at the same time. But obviously, if you can find any upper bound and any lower bound, then you can find a single one, which is an upper bound, and then the negative of it is also a lower bound, right? If you just take whatever one of the two upper and lower bounds has a bigger absolute value, you can use that one. So that's boundedness of sequences. Also, you can just make the same kind of definitions for like specifically bounded above or specifically bounded below. But in general, well, for sequences, they can only be unbounded. Actually, no, they can be unbounded in both directions. Sorry, never mind. Anyway, so yeah, so you can make the same definitions to call a sequence bounded above or bounded below specifically. You might have a sequence that's only bounded above or only bounded below. Okay, so let's state our theorem about boundedness. So this is theorem 9.1 in the book. Convergent sequences are bounded. In other words, if a sequence converges, then it is bounded, if you really want to make sure you phrase it as an if-then kind of statement. So here, so let's prove it. Now, remember, so here is a situation where convergence is a hypothesis of the theorem, right? So it's if it's convergent, then something else, right? So in the proof, we're not trying to prove convergence, we have to use the convergence to prove something else, okay? So what we want to say is let Sn be a convergent sequence. Say Sn converges to a number S, okay? Now, let's think about what we can do. So the only thing we really know about the sequence is that it converges, right? What does that let us do? It lets us, remember, pick epsilon and find capital N such that for that epsilon, everything stays within epsilon away from the limit value s after capital N, right? So in this case, all we need to do is just use that to control the size of the terms in the sequence, right? As soon as you pick epsilon, right, anything that has to stay within epsilon of s, you know it's like bounded above by, you know, absolute value of s plus epsilon or something like that, right? Like it can't get too far away from 0 if it has to stay within epsilon away from s, okay? That's the key. It can't get too far away from 0 if it has to stay within epsilon of s. So all we have to do is pick any value of epsilon, actually. It doesn't matter which one. And then deal with like the initial terms separately. So let's just pick epsilon equals 1. And this is a totally arbitrary choice, so I'm going to put an asterisk here. So then, because Sn converges, there exists a capital N such that for all n bigger than capital N, we have Sn, and sorry for so much dense notation, but it's just easier to write that way. So Sn minus S, absolute value, is less than 1. Okay? Okay, so here we have Sn has to be, so for these values of n, Sn has to be within 1 of S, okay? So here I'll try to illustrate a little picture. So what does this tell us about the absolute value of Sn, right? Let's draw a little picture. So there's sort of two cases, right? Case one is S happens to be negative. So let's say S is negative. Then how far away from 0 could Sn get, right? Well, the worst it could do is to go over here all the way towards S minus 1, right? Then the absolute value of Sn would really just be whatever the absolute value of S is plus 1, right? It's basically saying that Sn, the furthest away Sn could get from 0 is however far away S is plus 1, right? We went 1 further away from 0 in this way. And then the same thing happens in case 2. If you have S over here, then S plus 1 is the farthest away that Sn could get, right? But in either case, that distance is just the distance of S from 0 plus 1. So in other words, in symbols, right, this is saying that Sn is less than the absolute value of S plus 1. And we can actually justify this bound here with the triangle inequality. So we can say that, you know, Sn equals Sn minus S plus S, which is less than or equal to Sn minus S absolute value plus S absolute value, which is now less than, because this is less than 1, we have 1 plus absolute value of S here, right? This was the triangle inequality. I don't know how to abbreviate that. And then this was our assumption about how we chose capital N. So this is for n greater, or n, n greater than capital N. So then all that's left is just, you know, so we have basically what we have is an upper bound on the absolute values of Sn for all of the values of n after n, capital N. But we don't know anything about the ones before capital N, but there are only a finite number of them. So basically take M to be the maximum of, you know, S1, S2, and so on up to Sn. So that deals with the first n terms, and then 1 plus absolute value of S. So then M is a bound in this sense, right? All of the absolute values of Sn for every value of n are less than or equal to M. Again, there are common themes here already recurring, right? Which is that we use the convergence to deal with all but a finite number of terms at the beginning of the sequence, right? Very classic pattern, this is often what you do, is that you concern yourself first with like the tail. You can call that the tail of the sequence, is kind of like all of the terms of the sequence after a certain point, you can call a tail, or the tail of the sequence. So we look at the tail of the sequence first, we deal with that, and then there are some scattered values at the beginning that we don't really care about. They're easy to deal with, right? Classic thing. So that's all for this section. In the next one, we'll talk about adding and multiplying sequences.